And thank you very much for the introduction, and thank you very much for inviting me to come and talk to you. Hope this is of some interest to you. So I have to perhaps put a declaration up front. I'm not an actual researcher into cold dark matter. I'm more of a user. My research is basically in simulations, and we usually use cold dark matter as our base for simulation because well, I'll talk about that as we go along, the reasons why. So I was going to ask, split this into three parts. First question is, why do we believe it exists at all? Because it does feel rather like it's something we've just made up. The second bit is, if we do believe it exists, if I manage to convince you it does exist, then what do you think it could be made of? And the third part is, if we follow on from those two, how can we actually go about finding it or getting our hands on some and doing something with it? So those are the 3 points I'd like to cover. And this is basically what the universe consists of. So dark energy, we really don't know very much about that at all, but we do know its name, so that's a start. About 72% of the universe, or 68%, depending on which survey you go with. Dark matter is about 23 to 25% of the universe, somewhere around there. And the regular stuff that we know and love, atoms and everything we have researched up to sort of 20 years ago, is about 5%. So it's a little embarrassing that we've only been studying 5% of the universe in astronomy for many, many years, and we've just sort of caught up. There may be more stuff to find out. So the obvious question is this really the case? Or is it just that we've run out of ideas in astronomy, so we've had to make something up to extend the funding grants or something like that? So there's this very nice cartoon that says, you know, after the discovery of antimatter and dark matter, we've just discovered the existence of doesn't matter, which has no influence on the universe whatsoever. And that is somewhat like dark matter, except there is a certain amount of influence from dark matter. All the strange conspiracy theories you can find out on the net if you go down sufficient rabbit holes. So is it really all a scam? That's the question that I'm hoping to convince you that it isn't, that there is some seriousness behind this. And just to sort of set the scene, obviously this isn't going to prove anything, but we have been here before in physics. In the 1930s, Pauli proposed a new particle called the neutrino because certain atomic reactions were not behaving properly. They were not preserving momentum, they were not conserving energy. And either we had to sort of throw away the whole idea of conservation of these laws, or he bravely came up with a new particle, which he called the neutrino, for the little neutral thing. And it was, have to say, a very brave step. You know, he said, "I have done a terrible thing. I've postulated a particle we cannot possibly detect." But it balanced all the books and you know, made all the theory right. It's just undetectable. But you know, in the meantime, we have worked hard, and in 1956, the first confirmed detection of the neutrino was carried out. So that was what, 26 years that we sort of lived on faith that the neutrino existed. More recently, 1964, Peter Higgs postulated the Higgs boson to give certain particles mass. And luckily for him, he lived long enough to actually see the detection in 2012. So again, we lived for many years sort of hoping that this thing did exist and that it fixed all the equations and all that sort of thing. But there was no sense of actually detecting that. Dark matter we haven't done quite so well. So it was proposed in 1932-ish, we'll come back to that, as a possible thing. And to cut a long story short, and you could probably all just switch off and go home now if you're not that interested. We're still waiting for an actual physical detection of it. We really only detect it by gravity. So there isn't going to be a big reveal at the end, just in case any of you are waiting for it and say, we found it and this is what it is. So that's where we are anyway. And cosmology, which is the study of the entire universe, really relies on both the idea of dark matter and dark energy at this point. It's very unusual for anybody to propose a paper or anything else that doesn't rely on both of these things these days if you go into cosmology. And in particular, a thing called lambda CDM. So lambda is the dark energy bit and CDM is what I'm going to talk about tonight. I will mention a bit about lambda, which is basically all I know, so it's only about a slide and a half. But having said that, even the experts on it could probably only go on for 4 or 5 slides. So lambda CDM, the current model of the universe, this is the lambda, Greek lambda, which is the dark energy term, and CDM, cold dark matter. And you'll see this in all papers, so you know, whatever you're talking about, there's one of mine, in fact, n-body dark matter lambda CDM simulation. So pretty much everybody, if you go to the big enough scale, talks about lambda CDM. So well, let's talk a little about that. So here's lambda, and it does appear in Einstein's field equations, which you may or may not recognize from here. To forestall any questions, this is about as much as I can tell you about these field equations. They are phenomenally hard to solve, and I've never tried. But the two sides of the equation, one says this is how space curves, and this is, the other side says how matter behaves. And there's this lambda term in which was in for a bit, then out for a bit, and it's now back in. And this is the expansion term for lambda. And this does lead to future fates of the dark energy universe, because we've no idea whatsoever what this lambda dark energy is. There are at least 3 possibilities. One is that the universe will collapse in on itself and come to a big crunch. This is a sort of time modifying version of dark energy where it's in forward gear at the moment, but at some point in the future it will go into sort of reverse gear and suck everything back together. Not sure how popular that theory is at the moment. Sort of the medium one is indefinite expansion. The universe is expanding at the moment and will just continue to expand and actually accelerate slightly. But that's the universe as a whole. And the final one is the big rip, and this is where dark energy actually kind of speeds up somewhat and gets stronger and stronger, and eventually starts ripping galaxies apart, and then starts ripping stars apart and planets apart, and finally atoms apart and everything. It just goes crazy, and that is the big rip where everything is ripped to shreds basically. And the most satisfying idea for dark energy is that it's this thing called vacuum energy, but unfortunately when you do the calculation for this, it's off by this sort of factor. So that's a worryingly large amount of zeros to have to cancel out in an equation, and you've got to sort of cancel them out almost exactly. So people are looking for other ways around this, and quintessence is one of the popular things. Sort of comes from earth, wind, fire and water, and this is the 5th force, or the fact that we have four known forces of strong, weak, electromagnetic and gravity at the moment, and this could be a 5th one, or it could be something else, or it could be, there's all sorts of ideas, and there are a couple of people in our department researching this, and they could talk a little more about it, but realistically at the moment we have absolutely no idea even where to go looking for it. So a lot more work needed there. So that's all I know basically about the dark energy side of the universe. I know a bit more about CDM, although I said I'm really not an expert. So why is it called CDM, cold dark matter? The cold refers to how quickly it's moving. So there is another theory called hot dark matter, which is now no longer in favour. And in hot dark matter, it's stuff that's moving at about the speed of light. So everything is moving extremely fast. Cold dark matter could be moving quite quickly, but it's not going anywhere near the speed of light. It's not anywhere into the relativistic framework. Dark is just the fact that we can't see it really. So it doesn't matter how hard you shine a light on it, it will never see it because it just doesn't work with light. And the matter sort of comes from the fact that it's probably going to be a particle rather than just sort of radiation, rather than waves floating around. Although, you know, in reality, all these things are up for grabs. This is just where they sort of the good money is going at the moment. That we're going with cold, dark, and matter as the things which I don't think are particularly good explanations, but we're not going to change them now. So this pie chart is what we started off the universe with. So you can see there's no dark energy, at least in this variation at the beginning, just after the Big Bang. So it's sort of 5-to-1 atoms to dark matter and a sprinkling of other things. And then today we have this sort of, this is from the Planck results, dark energy of 68%, dark matter 27%. The regular atoms somewhere around 4 to 5%, of which most of it is gas floating around, not doing anything much. 0.5% of the universe is in stars, and 0.03% is in anything interesting beyond hydrogen and helium. So you know, this Earth and you and me are basically sort of flotsam of the universe, the leftover bits. So where did it all start? Where can we pick this story up from? So the very first start comes from Jan Oort, a Dutch astronomer, which you may have heard of from the Oort cloud, he gives his name to. Did quite a lot of work in various parts of astronomy. But in 1932, he was looking at the proper motion of stars, how the stars are moving around the galaxy. And he was doing this to try and work out about where the center of the galaxy was and where we were in our position of the galaxy. So he was measuring how fast the stars were moving, sort of internal to the sun, between us and the center of the galaxy. And he did reasonably well with this and came up with a number. But whilst working this out, he found that he could only find about a third of the stars he needed to keep us in our position in the galaxy. You need a certain amount of gravity within the galaxy, within the sun's radius around the galaxy to keep it contained. If there isn't enough, then the sun just goes flying off into intergalactic space. So he said there's a bit of a problem here. I can only find about a third of what's needed. So there's stuff missing. And he assumed it was probably very dim stars, things like we now know are brown dwarfs and things like that, or extra dust and gas or things like that. But it is quite a lot you need. It's for his calculations, which weren't terribly precise, you needed 3 times as much as he could actually see. This was taken much further with Fritz Zwicky, who was a very, very colourful character, very, very bright, but not very good with people skills, famously calling his fellow astronomers in California spherical bastards, because they were bastards whichever way you looked at them. You can imagine that didn't go down terribly well with the faculty. But he did a lot of really good work early on. He did quite a lot on supernovas. There's another STEM he worked on, which I've forgotten. But dark matter is perhaps what he's most famous for, although he's quite well known for supernova work too. And he did the work looking at this cluster here, which is the, I've just forgotten what it is. It'll come back to me. Cluster of galaxies. Fornax cluster. I think it's the Fornax cluster. Might not be, might be. No, it's the Coma cluster. Oh, what a thing to forget. So this is the Coma cluster of galaxies. You can see this cluster of galaxies here, and they are all gravitationally bound, so they are all sort of connected to one another by gravity, and they're all sort of moving around each other, a bit like stars moving around a galaxy. And he found a way to weigh them. In fact, he found two ways to weigh them. And one way is you look at the light coming from them, and you can roughly work out that if you know how far away it is and you know how much light there is coming from the galaxy, and you work out on average, it turns out our sun is about an average star for the amount of luminosity it gives off to an approximation. So if you work out the amount of light coming from a galaxy and say, and I know how far it is away, so this is about how many suns would need to provide that. That gives you one way of working out the mass. And he came to 10 to the 12 solar masses. But you can work it out in another way, which is looking at how these galaxies are all moving around one another. And as long as they are what's called virialized, which is they're sort of settled down into a steady state, all moving around, they're not all just collapsing in or exploding out, then you can do another calculation. And looking at this calculation, he came out with 10 to the 14. So this is a factor of 100 different. So by looking at the starlight, he comes up with one figure. Looking at how they move, he comes up with a figure, a factor of 100 difference. Now this is quite hard to explain. You need either another 100 galaxies, or you need a lot of extra stuff to fill in this gap. So he came up and said there's a lot of missing dark matter, called it Dunkel material, because he was a Swiss German, but did most of his work in the US. So that was 1933-ish. He came up with and coined the phrase dark matter, and it's sort of stuck ever since. But it was largely forgotten about after that. There was a guy whose name I can't remember, began with H, did some work in the 1940s, but that was largely overshadowed. But it wasn't until we got sort of better telescopes and we started looking at things, and in particular looking at the velocity of how things move. So this is standard what's called Keplerian orbits for things, and you might know that Mercury goes around the sun very quickly, 88 days. Pluto goes around in, I think it's 239 years. So this is just a result of the fact that most of the mass in the solar system is all sitting in the sun. So anything close to the sun has to whip round pretty quickly, otherwise it will get dragged into the sun. Whilst if you're out near Pluto, the gravity has dropped off so much that Pluto can just dawdle around at that distance and doesn't really need to be shooting around very quickly, because the effect of the sun's gravity at that distance is quite small. You can do the same thing with galaxies. They're a little more tricky to do because not everything is in the center of a galaxy, but quite a lot is. And this is the sort of famous rotation curve of M33 measured. So if you work out, basically again taking where you see the most light is probably the most mass, and you say roughly that you'd expect this is what the speed would be, you would see the broken dotted line, the expected from luminous disk. You would see that sort of profile of the speed of stars going around the galaxy, that as they get further out, they should slow down quite a bit. But that wasn't what was seen at all. The top line is what was observed with error bars, and you can see it's quite somewhat different. So that's a big gap you've got to explain, and it's not just one measurement. You can't just sort of say, well, that was one measurement that was off, we're going to take that a bit more carefully. There's quite a lot of measurements there you've got to explain. And Vera Rubin, who was somewhat overlooked at the time, except by astronomers, but is now somewhat more famous, extended this much further out. Looking at further distances, you can, rather than just looking at stars, you can look at gas moving around Andromeda and take this much further out. But again, the observed orbital velocity is more or less constant for a long, long way out for Andromeda. Your prediction from what is visible would tail off very quickly. So there's a lot of missing stuff that It's just not there. And without this, the outer stars should not be where they are. They should be no longer attached to the galaxy. They should be flying free and zooming off and doing their own thing. So that was a couple of strands that really started people thinking that there was something missing here. The next one came from something called Big Bang nuclear synthesis. And this is looking at nuclear equations, basically, in the very early universe. And in particular, what happened at the Big Bang. And Fred Hoyle, who's pictured there, did quite a lot of this early work. So very soon after the Big Bang, in fact 3 minutes after the Big Bang, the whole universe is behaving much like a large star, and it's actually fusing hydrogen into helium and doing what our sun does, basically. But it only does this for 17 minutes, because then the universe by that point has expanded sufficiently and cooled down sufficiently that these reactions can no longer happen. And there's a whole load of reactions that are happening there that you can follow in this flow chart if you're really, really interested. But don't worry too much about them. But they're just saying things like deuterium would fuse into helium-3 and helium-4, and you might also get lithium and beryllium and tritium and all these other very low number atomic elements. And you can actually calculate exactly what would happen if you put a load of this into a mix and then just let the nuclear reactions go. This is fairly well understood nuclear theory, and you can just plug the numbers in and see what you would expect after 17 minutes, how much relatively of each these you would expect. And the only thing it's really dependent on is how dense the universe is at that point. So if you feed all that into equations and do them, you come up with this graph here. And then you can go out and measure these things in the universe. And that's what they've done with this. I hope you can see the cursor. So this is the amount of helium-4 measured, deuterium, helium-3, and lithium. So you can go into bits that are untouched in the universe and try and measure what the original mixture of this was from the Big Bang. And you get the best constraint actually from deuterium, which is this one here. And that gives you a very narrow band of how dense the universe is. And you can see the density across the top. And this gives about 4 to 5% density of atomic stuff in the universe, meaning the rest is something else. And this actually lines up very much, very nicely with the calculations from that came out of Vera Rubin and other people, which also said you need about 5%. Well, you need about 5 to 1 dark matter to regular matter. So this is like another angle that you're coming at this from that is not really connected with galaxies rotating or anything like that. Another one comes from formation of galaxies, that if you sort of run the Big Bang model from very early stages to where we are now, soon after the Big Bang has finished, and say about 400 million years after it, stars start to form and then galaxies start to form. But if you put this all into a computer model, it doesn't quite happen like that. The stars and galaxies don't really start to form until a long, long time after this, many millions, billions of years. But if you add this dark matter component that we sneakily suspect exists, and you put it in the right mix, then everything collapses that much quicker, because you've got a lot of this dark matter to collapse very quickly, and this drags everything else in and lets galaxies construct much earlier on. So we've run lots of these with computer models. If you don't put dark matter in, you don't get the universe we see, at least not yet. You might get it in billions of years hence, but you don't get it right now. If you do put dark matter in at just the right mixture, so it's a bit like a recipe, 5 parts dark matter, 1 part of regular matter, then you get, in a computer model, something very similar to what we see in the night sky. So that's yet another strand of evolution. So that's kind of where this comes from. You get enough time for the galaxies to form, because the universe is still very hot up to this point around here, and it hasn't really settled down and started to collapse into galaxies because it's still very hot. But the dark matter is completely unaffected by this heat, and it just settles down and starts forming big pools that you can't see of very concentrated dark matter into which the regular matter falls. So it gives it kind of a head start. Another strand comes from gravitational lensing. If we went back to Einstein's field equations, they predict that light is bent around heavy objects. This was proved in, was it 1917 eclipse? 1919 eclipse. I always get those two mixed up. But anyway, it's been proved many, many times since that light is bent around by heavy concentrations of mass, and you can do this not only with stars such as the sun, but you can do it with galaxies, and galaxy clusters are a very favorite thing to do it with because they have a lot of that. But the same problems occur there. And this is one of those. This is a gravitational lens, so this is a single galaxy gravitationally lensing a distant one. So the blue smeared out bit is a galaxy as viewed through one of these gravitational lenses way back, much further away behind this sort of orangish elliptical galaxy. But again, you can do the calculations and you can work out roughly how much mass there is in that elliptical galaxy, and there is not enough to bend the light as much as it's being bent. So again, you come out with it needing to be about 4 or 5 times as dense as it appears there to bend the light through the amount we're seeing. So this is yet again another evidence. This is another case of gravitational lensing. You can see this one's not quite so clear. This is done by galaxy clusters, but you can perhaps see streaks across this thing, particularly here and here. It's all being streaked out, so this is very, very distant galaxies being bent around this cluster, but it's not quite so clear because the mass is all sort of spread around. But perhaps the best comes from some very clever maths that I'm certainly not able to explain, but it comes from this cosmic microwave background, so the study of this remnant of the Big Bang at 2.7 degrees Kelvin. So if you map the sky in this, you can pick up this structure of it, and you can see it's slightly speckled. The red bits are slightly hotter than the blue bits, but only by a very, very tiny amount. But nonetheless, there is information buried in this structure, which you can extract. Well, you probably can't, I probably can't, but people cleverer than us probably can, well, certainly can, or big teams of people actually work on this. And this is what they extract. This is the usual way it's shown. It's a little difficult to explain, but basically this scale across the bottom is how similar things are. So this is looking at very big things at sort of 90 degrees from each other. If you look at two things across the sky 90 degrees apart, very big things, then how similar they are they? This is not very well constrained because you can't see very many big things in the sky 90 degrees apart. But as it comes down, as you get to about 1 or 2 degrees, you suddenly see there's a big similarity between things across the sky in this microwave background, which gives you this peak here. And then you get a few more peaks that sort of gradually wiggle away. And in this plot, the green is the theoretical line calculated from equations, and the red is the actual data taken by, in this case, Planck mission matched to that. You can see it's a phenomenally good fit. We don't usually get lines to fit nearly as well to the data as this, but because of the accuracy of the instrument, this was a particularly good fit. So what does this tell us? Well, just trust me on this one, because I probably couldn't explain it in very much more detail than this. But this big peak here tells us that the universe is largely flat. And this means that it's not curved around onto itself. If you set off in a direction in a spaceship at a huge speed and carry on for as long as you can, this means you will probably never come back to the same position. a bit like going around the Earth, you know, which we were just talking about with light seconds. If you set off around the Earth, you will eventually, and keep in the same direction, you'll eventually come back to where you are. We don't think that's the case for the universe. It's flat based on this peak, and a fairly good approximation. Now, these next two peaks tell you about baryonic matter, which is atoms, and dark matter. And it's not particularly one or the other, it's the ratio of one to the other that tells you how much dark matter to baryonic matter. And by working this out and fitting it to models, you can work out how much of one there must be compared to the other. And this was done, this is a moving graph here of, you fit various parameters to it and you can sort of see where things line up and where they don't. And so you can tweak this equation around until it fits with the data, and it fits best where there is 5 times as much dark matter to regular matter. So that's some of the lines of evidence. There are a couple more lines of evidence that say dark matter should exist, but they're getting a bit more esoteric at that point, and my ability to explain it is also getting more esoteric, so we'll stop at that. So there are 2 possible ways to fix it if we believe this is the case. First is to say, well, gravity doesn't really behave like we think it does. There must be some other way it works. So we could go about doing that. We could tinker with Einstein's equations. The big problem with that one is we've tested Einstein's equations in many, many cases, and they always seem to work. So the wriggle room for slipping tiny fudge factors into that equation is very, very small. You can certainly go and mess with the equation, but it still has to work in all the cases we know it works. And that's very difficult. It's like drawing a straight line and saying, well, I need to take this point in that's way off the line. How can I squeeze that in? It's not easy. So the other option, which most of the astronomical community have settled in on, is that there's a whole lot of missing mass. There's a whole lot of stuff there that we can't see and can't detect. And this just fixes everything if we go with that. And there are various explanations for this. One was machos, another was neutron stars, another was black holes, extra gas, and brown dwarfs. These have all been proposed as simple fixes. These are things we know that could possibly fix the problem. Now, most of these have now been largely rolled out. They're all possible things that they could be. And in fact, one of my colleagues is still working on the black hole idea, that there could be small black holes floating around that would fit the bill. That is kind of running out of steam. It's still possible that it could be these black holes that were formed in the Big Bang that are actually making this, but the sort of space that these could exist in is disappearing. And the other issue is that we should have seen these. Most of these things are really, really dim, or in the case of black holes, black. So you can't actually see them directly, but you can see them through this concept called microlensing, which is gravitational lensing, just like we saw earlier on, but working with very small things. So you look at something distant, and this example is looking for exoplanets. So you look at a distant star, and something moves between you and that distant star, and you can see what happens to the light as this happens. It begins to amplify the light, and in this case there's also a planet, so you get a big spike where there's a planet, and another much bigger spike where the star has really focused the light, and then it fades away over this way. So that works as a good technique for finding exoplanets. You can use the same thing with distant stars in distant galaxies or Magellanic clouds to see if there is stuff floating around in our own or just outside our own galaxy that we can't see. You should see the same signatures, and it doesn't matter whether it's a bright object or a dark object. You'd still get this, this sort of magnification. And there's been a couple of searches for these sorts of things, and they have come up with objects that do fit the bill, but only a very few of them, not nearly enough. And if you remember back, we need about 5 times as much 5 times as many objects as we know there are stars in the galaxy. So that is a lot to find. So even looking just for a short time at a short patch of sky, if you're going to explain dark matter with these things, you would need to see lots and lots of these things going past and doing this microlensing, and we didn't see enough by anywhere near the amount that we would need. So we kind of crossed that one off. So what are we looking for? It has to be something that's stable. So we needed it at the Big Bang to form galaxies early on, and it still has to be around. So it's probably not something that decays like radioactivity or something like that. Or if it does, it has to be a very slow decay to still be around. It has to be electrically neutral for various reasons. The main one, we would be able to see it otherwise. It has to influence gravity because that's what we saw. And obviously not to be visible, otherwise we would have seen it by now. And the sort of scale we're looking for, so this is a typical galaxy, the dark matter halo is about 10 times the size of the galaxy. So dark matter clumps, or it originally clumped together to form these sort of gravity wells, as we call them, into which the regular matter falls. And they're still around, and they're about 10 times as big as the extent of the galaxy. So if you could look out into the night sky, so this is a nice picture of the moon in the night sky, and if you could see Andromeda next to it, you know that Andromeda is quite large in extent, although you need an extremely good telescope or a good camera to capture the full extent of it. You would see Andromeda as much bigger than the full moon. But if you could see actually the dark matter, you could see the dark matter halo around Andromeda. You would see it sort of dominating the dark sky. Unfortunately, we can't see that. We can see the influence of it. But that does let us explain this joke, which you may or may not be laughing at. So this is the dark matter halo around a regular halo of a saint. So this would be a 10 times bigger halo around a saint. That's probably enough about that. Now I hope this video comes out. So this is done by someone, and I tried to find out who it was, but I couldn't. This was uploaded to YouTube. So at 500 million years, he takes away the dark matter from the galaxy, and you can see everything within outside of a certain radius just flies off into outer space. So that is what Jan Oort and Vera Rubin saw, that stuff should just be flying out into outer space because there is not enough gravity within a galaxy to hold all the stars in. So yeah, don't try that at home. That would be bad. I did mention hot dark matter. So this is just the difference. Cold dark matter moves relatively slowly. It might be going quite fast for us, but it doesn't go at the speed of light. But this does result in certain things. So cold dark matter would grow together in small lumps, and then these small lumps would sort of grow hierarchically. The small lumps will grow into bigger lumps, and bigger lumps will grow into bigger lumps, a bit like how planets formed. If it was hot dark matter, then you would get extremely large clumps forming when they did, and then they would split up into smaller things. Hot dark matter would be very well explained by neutrinos, but as that is not the universe we seem to live in. That's bad news, because that would really fit the bill. But we know it's now not hot dark matter because we see all the signatures of cold dark matter. So we've probably ruled out regular matter at this point for cold dark matter, so it must be something more exotic. However, hot dark matter hasn't been, well, it has been ruled out, hot dark matter, but there is a slight anomaly. So this is a simulation done at Durham, of which there's lots and lots of these simulations done. So this is forming something like the Milky Way. That bright spot in the middle would be the Milky Way. And you can see all these sort of fainter bright spots around it. So this is a dark matter simulation, and we get the big concentration around the Milky Way, but we get lots and lots of these other spotty bits around the Milky Way, and these would all be dwarf galaxies or things like that. And the problem is, if you do the simulation, you end up with about a factor of about 3,000 of these little things drifting around the Milky Way in the current time. And to our best searches, we maybe got 100 to 120 of these things that are floating around the Milky Way that would fit the bill. So that's a little bit of a worry, called the missing satellites. Where are all these missing satellites that are predicted by simulations, and we can't find them? So one solution is to make the cold dark matter a bit warmer. And so you end up with something called warm dark matter, or tepid dark matter, or slightly heated up dark matter. This does fix the problem. You can see there you get many less satellite galaxies, but you end up with all sorts of other issues. So you've almost jumped out of the frying pan into the fire in this case, that you can fix one problem, but you get a whole load of other issues that come up from that. So if we're convinced that it could be there, what could it possibly be? And you might think this is an issue that we've sort of found everything that we've been looking for. We just ticked off the Higgs boson as the last sort of missing thing. So perhaps we're struggling to find anything. But oh no, you don't get off that easily. Certainly not if you're in particle theory. You can come up with any number of things. So what could it be? There are papers and papers on what it could be. So the possibilities are something called WIMPs, and these came up perhaps early on as an alternative to these MACHOs, massive compact halo objects. So these are weakly interacting massive particles. So you get MACHOs and WIMPs, if you get the joke. So WIMPs is certainly one, of which neutrino is a possibility. Stereoneutrino is another one. Then there's a different type of thing called an axion. There's the graviton that we hope exists. And there's a whole dark sector that could possibly exist. Then there's a macroscopic quantum resonator. These are getting increasingly weird, I have to say, at this point. There's some things called Q-balls, fuzzy dark matter, WIMPzillas, and at this point, you really do think they are just making them up. But no, these all have scientific papers written on them and theory behind them. In fact, in some cases, they have several people writing papers on them. So yeah, these are all possibilities, and I'm going to explore a few of these. I'm not going to go into all of them, which you'll probably be relieved to hear. So they're often plotted on a picture like this. Now this just needs a little bit of explaining. I hope I've got the explanation. So up this y-axis, this is how wide the particle is, or a better way perhaps is how easy is it to hit it? How easy is it to collide two of these things together? So this is what's called the cross section. And along the bottom, we have, oops, gone too far. Get back to that. Yes, along the bottom, we have how heavy is this particle. So I've plotted on here, up here in sort of orange balls, is the electron and the proton. So because they're up towards the top of the graph, they're pretty easy to hit. So I can hit the desk here, and that's because these things are pretty easy to hit. As you move down the graph, they get harder and harder to collide. So they would just tend to go through each other as you go down the graph. So you can see down here at the neutrinos, these are very, very difficult to hit. And that's why it took so long. They are very ghostly. They hardly ever want to interact with anything. So they were very, very hard to find, and we're still not great at detecting them. The biggest neutrino detectors on the Earth detect a handful each day. So like, 10 at a maximum maybe a day of neutrinos. Despite the fact that there are billions and billions a second going through the neutrino detector, they only find 5 that actually collide with matter. So you can see here WIMPs, which is in this purple block of where WIMPs could exist. They're much harder to detect by about a factor of 1,000 than neutrinos. We already know neutrinos are really hard. If you go down to other things like axions and gravitons, they're just getting ridiculously, stupidly hard to detect. Because these are log graph. Every step down here it's 10 times harder to detect. Then this is the mass. So this is the mass of the electron, the mass of a proton. in giga-electron volts, and you can go all the way up here to black holes. Black hole remnants are very, very heavy, and all the way down here to fuzzy cold dark matter, which is extremely light. It's really hard to sort of overemphasize what a huge scale this is. This goes from stupidly light to stupidly heavy, and stupidly easy to detect to stupidly hard to detect. So that's the sort of level you're working with. But let's just have a look at a few of these. So the first one is the neutralino, and this comes out of something called supersymmetry, which is a very popular theory, has absolutely no evidence for it whatsoever, but it is very mathematically appealing. So that's kind of why people are looking at it. And this says that all the basic building blocks of everything, so this is the building blocks of everything here. These are quarks over here. So these are the things that build up atoms eventually. And these are neutrinos, and here's the electron and muon and tau. And then the force-carrying particles, this is the photon, the gluon, and the Z and the W, and the Higgs. So supersymmetry says, well, what if we have all those, but we swap them around? So for every one of these matter particles, or these sorts of things, quarks, there is a supersymmetric force-carrying particle. And for every force-carrying particle, there's a supersymmetric real particle. And as you probably know by now, I'm not into the maths of this, but the maths of this is extremely appealing. It means you don't have to make all sorts of assumptions, and stuff just drops out of the equations rather nicely, rather than having to put in strange constants as we do at the moment. So this is why it's very appealing. As I said, there's absolutely no evidence that this is true. But if it does, then you get this whole set of other particles that don't really exist in real life. This is completely different to antimatter, by the way. So antimatter is still on this side, so this is something completely different. So you get these SUSY particles, so you have to name them slightly differently. So these are quarks, but they're supersymmetric, so they become squarks. These are leptons, so they become sleptons because they get an S in front of them. And the things that were force particles, they get enos added on to the end. So this is the photon eno, or photino, the gluino, the xeno and the wino, or wino, and the Higgs eno. So, as I said, there's no evidence for all these to exist, but if they did, just supposing they did, then there is a certain particle that comes out from these called the neutralino, and this is the least heaviest stable particle. So this is basically everything would decay into the neutralino by and large. So you get, in the Big Bang, you presumably get lots and lots of these things, but they would all decay back into the neutralino by now. And this would be a perfect candidate for dark matter if only it existed. But as I say, there is absolutely no evidence whatsoever that it exists. Another thing is called the axion, or axino, if you want. It's a supersymmetric particle. And this came out of something called quantum chromodynamics, which is basically how nuclear stuff works, and was predicted in 1977, and is a bit like supersymmetry for quantum chromodynamics. If you just go with the stuff we know, you have to put in a lot of assumptions and a lot of sort of tweaky constants to make it work. So Pecky and Quinn came up with this idea of an axion as another particle, and said, if this existed, then you don't have to make up any of this stuff. Everything just drops out of the equations and it's all nice and simple. So it's extremely appealing to have an axion exist. And it just so also happens to fit the bill as a possible thing. And people have thought they've detected axions, and then they've thought they haven't. So this is yet another one to put on the pile of no evidence whatsoever, but very appealing. Then we have a neutrino. So as I said, we've already had the neutrino, and this has been rolled out as hot dark matter because neutrinos travel at the speed of light. But when we look at the neutrino in lots of experiments, there's something a bit strange about these. Nearly every other particle has a left-handed and a right-handed type. They sort of spiral to the left or spiral to the right. The neutrino doesn't. It always goes to the left, at least for its regular particle. It has a very tiny mass, the neutrino, very, very tiny. But this is got physicists thinking, well, if this always goes to the left, maybe there's a right-handed component of it. You know, there's a lot of mileage in symmetry. So maybe there is a right-handed version of the neutrino, which they call the sterile neutrino. And perhaps this has a small mass, a little bit more than the regular neutrino. But if it did, this would be a perfect particle for dark matter. Yet again, there is no evidence whatsoever that this exists. Then we can go into strange things. Lightest Kaluza-Klein particle, the LKK. And this comes largely from string theory, but other things too. And string theory proposes all sorts of strange particles that could exist. And these sorts of particles, they move between dimensions and they're very ghostly and so on. So you've got almost an open season on particles for some of these. So that's a possibility. And this is string theory summarized for me by Randall Munro from the XKCD cartoon, which I'll just read out. If you had an awesome idea that suppose all matter is based on energy is made of tiny vibrating strings. And he says, okay, what will that imply? I don't know. So string theory is yet another extremely appealing idea because it suddenly gets rid of all these point masses and point particles and singularities. But the maths of it is stupidly hard. It makes general relativity look relatively easy by comparison. And it is just kind of wonderful, explained to me by string theory proponents, that if you take the theory and you just sort of mess around with it a bit, gravity just appears out of the theory. You don't need to do anything, it just has to be there. And if you fiddle with it in another way, quantum mechanics suddenly appears. So it's a wonderful theory and a lot of people are very happy about it. But not only is there no proof of this theory, nobody even knows how to go about proving it at this point. So it's just beyond all our ability to prove. So that's kind of where we are. And these others I won't go into, Wimpzilla's cue balls, scalar gravitons and so on. Magic unicorn dust is one of my own, I just made that up. But I think it fits in quite nicely here, that it could equally be magic unicorn dust for all the proof we have of anything else. But this gives us a landscape of things that could be dark matter, and you can see where they kind of all fit into here, including some I haven't talked about, because there's various ideas that Higgs particles could also do this. This is supersymmetry up here, which is a huge area that you can fit all sorts of things into. Axions are down here, extra dimensions in string theory across there, sterile neutrinos over there, also warp dark matter. So, you know, it's not like we're struggling to think of something that could be dark matter. We have more than enough things that could be dark matter. We just don't have any proof of any single one of them. So that sort of concludes 2/3 of the talk. And the third part is, so let's assume it is one of these. Let's go looking for it. How can we possibly go about detecting it? And there are three ways, and these are often called the make it, shake it and break it ways. So these are ways you could actually go about trying to prove it in some realistic way. So the first part is trying to make it. If you bang together particles hard enough in large colliders, such as this is the Large Hadron Collider in Switzerland, then if you pour enough energy into it, you can actually make new things. So this comes from E equals mc squared. If you've got energy on one side, you get matter on the other, basically, E equals mc squared. So if you put enough energy in, you can make matter. So you can make exotic things by just pouring enough energy into things. You're limited here by the amount of energy you can shove into this Large Hadron Collider, and it's at about 13 tera electron volts, I think, at the moment, which is about as far as they can push it with the current technology. They'd have to build something bigger to exceed that. So this is this large ring that sent particles around and was built to go looking for strange new physics and also for the Higgs boson. So it succeeded in finding the Higgs boson. It has not succeeded in finding anything else new, unfortunately. So they're struggling a bit to get the funding to build anything bigger, because you basically go to the funding bodies and say, if we build something really big, we could find the Higgs boson, and we're almost certain to find some new physics, some new strange things that we didn't even know existed. And you go back to them and say, well, we found the Higgs boson. We're fairly sure we were going to find that. We didn't find this new physics, but if you give us a lot more money, we could build something even bigger and go looking for more new physics that we don't know exists. You say, well, how certain are you of finding that? They say, well, we're not sure because we don't know what we're looking for, but quite well we'll just be around the next corner. So it's a bit of a hard sell to try and do that. So you're probably going to only do that with big collaborations such as CERN, and perhaps bringing in lots of other countries to be part of that. But anyway, this is one way you could perhaps do it. So this is two quarks coming in. Well, this is a quark banging into a quark and giving off a gluon and a Z prime particle. And this might well produce two dark matter particles, whatever they turn out to be. The big problem with this is that you will never detect them, because dark matter particles don't interact, so they would just disappear. So you can only detect them by their absence. So you collide these things together, and you know how much energy you put in, and you work out how much energy is coming out of the reaction. Say, oh, there's a whole lot of missing stuff. And so that would give you a hint that there's dark matter being produced. Up till now, no sign whatsoever of this. I say they're also hoping to look for this for supersymmetry. Supersymmetry also predicts that you should lose some energy in this case. So they haven't found out there are those from this one. And string theory would also be delighted that you could see stuff moving between dimensions. Also not seen it. Second way is to go and look for dark matter bumping into regular matter. Now, as I showed you on that very busy graph of how easy it is to detect things, certain classes of dark matter are 1,000 times more difficult to detect than dark matter, and other classes are even more ridiculously hard to detect. So typically you would go deep underground, because otherwise you would be sort of swamped by detection of cosmic rays. And these you can sort of filter out, but you need to, if you can get rid of sort of 99.99% of all the cosmic rays, then you've got a lot easier task of trying to work out when you get a signal from a dark matter particle. So going deep underground gives you a lot of shielding from rock. So it's a lot quieter environment to work in. So they go deep down in disused mines and bury their equipment deep down in these mines, because that gives you at least a fighting chance. The idea is you'll look for one of these collisions, and the predicted rate is maybe once or twice a month you will find one of these collisions. So you've got to go and sit and look at this detector for once or twice a month events. Unfortunately, as I said, you also get lots of other things that will cloud the picture. So you'll get a few cosmic rays coming through. You'll get the odd radioactive element within the rock you're sitting in that goes off every now and again and sends a particle through your detector. So you'll have to account for those. You also get the odd neutrino that, well, you get billions of neutrinos going through your detector, but the odd one will occasionally bump into something in your detector. So you've got to get rid of all those things. So it's by no means an easy technique, and this is one of those that I do know a little bit about, because we had someone come and talk to us about this. So this is a liquid xenon detector. So you fill your detector full of liquid xenon at a very cold temperature, and then you wait for one of these dark matter particles to bump into your atom. And it works best with heavy atoms, which is why they pick liquid xenon. And this is the sort of thing you're looking for. Just once in a while, once in a month or two, a dark matter particle should come and bump into one of your nuclei of xenon, which is this arrow coming in here. And it will cause this atom of xenon to go scudding across the tank of cold xenon in this way. It will knock into other atoms and ionize them slightly. So you get a very tiny electric current, and you'll get a very tiny increase in heat governed by this reaction. Both of them phenomenally difficult to detect, but within the realms of the latest physics to actually detect those. So they could detect either of these, and they have the ability to do it. So they can sit there and run these, and they typically run them for a year or so to try and give themselves a fighting chance of detecting a few collisions, perhaps 1 or 2 collisions a month. And this is the latest results from these. Oh, well, these aren't the latest results. These are a couple of years old now. This is yet another very busy graph. And all these lines, the solid lines are, or they were, detectors that were running at the time, and dotted dashed lines are those that were planned at the time. And what they're doing is basically excluding search space. So if we look at this one here, COOP 2012, this says with about 99.99% accuracy, this line says dark matter cannot exist in this area of the graph. So this is going back to the graph I showed you with the detection regime. So it can't be with this, it must be a smaller cross section than this, 10 to the minus 43 in this case. So it must exist somewhere down here. And this is as much as we can do with this experiment. We can say it doesn't exist in any part of this. And we can go between 10 to the 4 and 10 gigaelectron volts. So that's the search space we're looking for. And this experiment rules it out from here. So it says, right, it doesn't exist there. Xenon, which is this Lux one, can rule it out from here. And as they get more and more sophisticated, they go deeper and deeper down here. So this is just started running Xenon 1 ton, and this is the area that they're hoping to exclude. And this pink circle here is where supersymmetry, one of the theories, predicts that it might be somewhere in here. So Xenon 1 ton can sort of start crossing off some of that area if it works out. And they just released some results actually about 3 weeks ago. Nothing to do with this. They spotted that there was another thing they could also work out from their experiment, and basically they've excluded some other areas. So up till now, all the experiments are negative, and they're just ruling out areas of search space. But it's a bit like they did with the Large Hadron Collider and the Higgs boson. They said it's got to fit somewhere in this region, and we can cut out this bit, and we can cut out that bit. So there's only this bit left. So we'll build the Large Hadron Collider that can probe that bit and see if we can find it. This orange bit is where things get really tricky, because at this point you can't differentiate between dark matter and neutrinos. And we know there's lots of neutrinos about. There are people who've looked at going below that, but you're going to have a hard time getting funding to go below that point to try and detect dark matter, because you're already well into the supersymmetry dark matter space. So it's like, how much money do you want to throw at it just to prove it doesn't exist there? Another experiment, ADMX, is looking for axions. Now these are stupidly hard to find by direct detection, but luckily axions have a secret up their sleeve. They do have an interaction with magnetism, so you can actually cheat at this and shine, well, it's effectively shining a light through the experiment. If axions pass through the experiment and then you put a strong magnetic field, there's a good chance, or well, it's not a good chance, there's a poor chance, but there is a chance that an axion would turn into a photon of light. So if you expect axions coming in from one side and you have a very sensitive detector on the other side and a strong magnetic field, you might occasionally see blips of light coming through basically what's a solid wall, and that would be detection of an axion. So they've run this experiment and they have not detected anything so far. So that's the second way. There are several more of these experiments around the world trying to detect dark matter. The third way is again, cheating somewhat, is to say, well, what we understand of the properties of dark matter is that it is probably its own antiparticle. So if two dark matter particles actually bump into each other, they will annihilate each other, just like bringing matter and antimatter together. The chance of two dark matter particles bumping into each other is very, very thin, because it doesn't bump into anything. It's just so, just such a tiny cross section that it just doesn't run into anything. So to give you your best chance of getting two dark matter particles to bump into each other, you should go looking where there is the strongest concentration of dark matter. And the strongest concentration of dark matter is probably in the very center of the galaxy, because that's where gravity is packing stuff in at the densest point. So if you go looking in the center of the galaxy, you might occasionally see dark matter particles colliding into each other with sufficient regularity that you see some particular signal coming from it, and it will probably come as gamma rays or X-rays or something like that. So you peer into the center of the galaxy with an X-ray or gamma ray telescope, and you look to see if there's a little blip coming from there that says, oh, that's unexpected, we didn't expect to see that. That could be the signal of two dark matter particles or a continuous dark matter annihilation happening. The big problem with the center of the galaxy is it's a very messy place. There's a supermassive black hole hanging out there. There's also pulsars, there's neutron stars, and all sorts of these other things. And they all produce signals of gamma rays and X-rays and things like that. So to actually go looking for this, you've got to say, well, how many neutron stars are there? How much radiation would they be giving off in the X-ray? How much will we get from the black hole? How much from that? We take all that into account with our best estimate. We measure the amount of X-rays and we take this off and see if there's anything left over. And lots of people had a go at this. Sometimes they come up with a blip and say, there you go, perhaps this is a signal of dark matter, only to be shot down next week by somebody coming along and saying, no, that's quite easily explained. That's just two pulsars circling each other would easily produce this. So you know, we know that can happen, so we'll go with that. So yet again, nothing has come up trumps on this. So that's pretty much the story of dark matter, rattled through in just over an hour. Sorry, it's gone on a little longer than it should have. But I'd just like to finish up with a couple of alternatives. So going back early on, I said you could tinker with gravity. And this indeed has been tinkered with, most famously by an Israeli scientist called Milgrom. And he came up with a theory called MOND, modified Newtonian dynamics, where you take the second most famous equation in physics, F equals ma, and you tinker with it a bit. And I won't go into all the details, but if you pick a new version of this, you can make galaxy rotation curves behave perfectly. This is somewhat cheating in some respects, because he has picked this equation and tinkered with it until it works. So you're sort of saying, well, what equation could we get to get it to work? And it has some good results. It will explain these rotation curves of galaxies perfectly. It will explain a few other things quite well. Some of the things it won't explain at all. And even in some of the papers that have been written, they say, well, it's sort of, you know, tick, 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 tick. It explains all these things, but we need some other sorts of dark matter to explain this thing. So a lot of people would rather go with just one type of dark matter rather than two types or two fixes. It does have some other issues. It doesn't really satisfy some conservation laws, such as momentum, and it doesn't really work particularly well with relativistic things moving at the speed of light, and there are a few other issues with it. So people have taken that and run with it. They've come up with things called Tevez, which Birkenstein did in 2004. He modified it to work with relativity. So this is a general relativity way of looking at MOND. But other people have pointed out that if you go this way, that stars may be unstable if you go with Tevez. So as I said, it's really difficult to tinker with general relativity because it works so very well. If you tweak it very slightly, you might well fix the problem of dark matter, but you see here other things occurring, such as stars may not be stable anymore. So other people have had other goes. There's scalar tensor vector gravity, biscalar tensor vector gravity. There's F of R theories of Einstein's equation. All these things are being actively worked on, probably not in the mainstream, but people are certainly working on them and running simulations to try and prove things. And this is good. This is how science should work. Most professional astronomers go down the route of dark matter, but it's as well to keep an open mind on these things. One thing that's quite hard to prove is the bullet cluster, and this is quite hard to get Mon to explain. So this is a galaxy out in in fact, I can't even remember where it is, but this is two galaxy clusters that have passed through each other. So you can sort of see one galaxy cluster here and another galaxy cluster here, and you can measure them by various techniques. This is a movie of the two moving through each other. So this is one of the galaxies sitting there, and here comes the other galaxy cluster, and it's moved through there. And the pink stuff is the gassy stuff that is certainly a major component of most galaxies. And gas is kind of sticky, and matter, dark matter, is not. But there's a lot of gas. Most of the matter is in the gas in the galaxy. So you would expect that to sort of follow it, but it doesn't. Most of the matter sticks in here. So the dark purple is where the mass is, and this bright stuff is where all the gas is. So most of the mass has followed the galaxies and not followed the sticky gas. So this is one example that is quite difficult to explain with that. So that's rather a quick, brief walkthrough of that one. So just in summary, going back to the three original questions, cold dark matter, is it cold? It probably is cold, but it could be warm. So we've explored warm dark matter and tepid dark matter. There's still an opening for those. Is it dark? This is probably a really bad idea, because it's not really dark. That sort of implies that you could just shine really bright light on it and you could see it. It doesn't matter how bright the light you shine on it, because it just doesn't work. So it's much more transparent. It's as though it's just transparent like glass or something. And is it matter? I think the jury's still out on whether it's matter, because it could be all sorts of things, including these primordial black holes to this fuzzy dark matter, which is much more like a field. So we really don't know at this point. But anyway, that's where I'm going to leave it. I hope that's given you a sort of an overview of what dark matter is and where it comes from. Happy to take any questions at that point, and thank you very much for your attention.
You could, Mark.
Yeah.
Can you hear me? If you'd like to lead the thanks, then we'll see if we've got any questions.
I was just wondering if, before I did that, whether there's anybody wants to raise their hands on the chat or ask a question to Julian about the talk.
I hope so.
Or whether why is totally silent.
Hopefully you have to. I may not be able to answer it.
I've got one question. If the influence of dark matter could be seen sort of at the level of galaxies, is there any more local influence? Can you see influences on, say, planetary movement within the solar system, or is that far too small an impact?
That is a really good question, and it is something people have looked at. But by and large, the dark matter is sort of smeared across the galaxy. So there would be slightly more, the sun would concentrate it a bit, but it's not really enough to do very much with. You can sort of work through the calculations, and you say it should make a slight perturbation to some of the orbits of some of the planets, but it's really, really tiny, because there's nearly as much outside the planet as there is inside it, because it's sort of across the galaxy. So people have looked at that and not found anything very evident, but it's a really tiny thing they're looking for. So I think we would have to get very much better at measuring distances to planets to be able to get, you know, down to very tiny errors in that to go very much further with that. But yeah, really good question.
Too small an impact then, really, at that sort of level.
Basically, yes. Yeah.
Accuracy measuring. Thanks.
I think a period under the chat for further questions, unless somebody wishes to raise their hand at all.
Well, while hopefully someone else is thinking of a question, I hope you will. I've got one for you, Julian. First of all, thanks very much. That was fascinating and very entertaining. I did spot your Shakespearean quotes, by the way.
No, did you?
I enjoyed those. And I was thinking, is he talking about cold dark matter, or is he talking about some cosmic game of snooker? Because we've got somebody called Higgs. I think there's a professional snooker player called Higgs. And then we've got machos, wimps and winos playing with a cue ball. So anyway, thank you very much. On the notion of velocities, of the observed velocities in galaxies further from the nucleus, have I understood you correctly in saying that stars are observed to move faster than the stars nearer the core, or just faster than they should be moving?
Faster than they should be moving, really.
Yeah,
faster to the amount of gravity to hold them in place.
But not faster than the center, because otherwise the spirality, if you look at a typical spiral galaxy, the spirality gives away the rotation, doesn't it? And you can see that the inner stars, to give that spiral shape in the arms, must be moving at a faster rate than the outer edges.
Yes, yeah.
So it's not a case of them going quicker, but they're going quicker than they should do, and they should in fact fly off, is what you're saying.
That's exactly the case.
Yes. For this mysterious CDM, yeah.
Yes, that's what's needed to hold them in place, or you fiddle with the equations too. Thank you, Rob B. Yes.
Yeah, fascinating, great stuff. Come on, everybody. I'm sure somebody's got a question. Yeah. You can put a question through the chat as well if you want. Don't be intimidated.
Yeah, I may not know.
There's a lot of maths in there, and but it was great stuff. Thank you.
I noticed from one of your early slides showing the galaxies, the picture you circled certain things. It looked as if you were circling stars rather than galaxies. This is the coma ones in the early part of your lecture.
Right, yeah.
If you can find it, I could understand all the galaxies that were obviously highlighted, but the ones that you circled, two of the ones you circled, appeared to be stars. Was I right or wrong? Or?
They should all be galaxies at that point, but yeah, I could work out how to work that. I found something. Get back to the coma cluster. That one there.
Yeah, the two at the top, the one at the very at the top and the one beneath it, they look like stars rather than points of light. It looks as if you've got the flares coming off it.
Yeah, they could well be stars, yeah. Nobody's ever spotted that before, so well done, yeah. Give you extra points for that.
Oh, thank you, Julian. As I said, I looked at it at the time and I thought, they look like stars. Anyhow.
Yeah, no, I think you're right.
Right, are there any more questions at all? If everybody goes down to the bottom of their screen, you'll see a thing called reactions. Mm-hmm. If you click on reactions, you will actually have a thumb up and a clap. And I would like you to show your appreciation for Julian's wonderful talk tonight. So, Julian, thanks very much again. It was most enjoyable.
Well, thank you very much. Thank you all for coming.
Well, thank you, Julian. It was wonderful. Excellent.
Right.
By the way, Julian, those two colliding galaxy groups. That presumably, am I getting this? That is an animation, is it, of what? We can't colliding groups of galaxies in real time over a human lifetime. So.
No, they take billions of years typically. So yes,
but it was very convincing.
That was a simulation done of the two. So we've just got a snapshot of it, but that has been measured. And
then just projected and just extended, extrapolated. Yeah.
So.
Fascinating stuff. Thank you.
They said progress with finding WIMPs? That was a question from Paul Thornley.
Yeah.
So that we're kind of well, there is no progress except we've excluded various areas of the search space. So the Xenon experiment, not what their acronym goes by, but they've just released new results saying we haven't found it here. So they've looked in new places and haven't found it, but they have found some other results that they think might be interesting. I think that was to do with axions, that they found that they could actually adapt some of the measurements they've taken could also explain perhaps axions. But unfortunately, there was a seminar on this that I missed. Otherwise, I'd be a little more up on that. So nobody has found anything apart from there was a. If I can go to that experiment somewhere, just find that one there. So on this one, you can see there's an experiment called Dharma, and there's also another one called Libra. Up here, this sort of, I don't know what color that is, sort of pinkish, grayish thing. And they did find a signal. They found a particular signal that, so one of the ways you can look for dark matter, because you only get very few particles per month, basically, is that half the year, the Earth in its orbit will be sort of going into the galaxy, and half the year it will be going out of the galaxy. You sort of see, it's like sort of running into the rain and running away from the rain. So you ought to be able to see slightly more effects through half of the year than the other half of the year. And they found, to a very good level of accuracy, that this was the case in their experiment. And so for a while, people thought they might have found it. That during half the year, there was a very, very different picture to the rest of the year. But nobody else could repeat this. And so there's this bit of an anomaly still. Nobody quite knows why this found, what they found. They clearly found something, but it's certainly not the dark matter everybody else is looking for. So it could be something entirely different. You know, it was to a huge level of accuracy they found this difference because they ran it over many years, but nobody else could repeat it with multiple other experiments. So whatever they found was probably specific to their experiment. So that's about as far as they got. And everybody else has basically said, nope, haven't found anything, but we can be sure it doesn't exist in this part of the spectrum. And yes, somebody said, yeah, Paul again said, yes, Bulby Mine near Whitby is one of the places they've certainly done. I don't know if that's still ongoing or not, whether they're still working that. Maybe Paul knows.
Yes, they are still working. We had a talk from the chap a couple of weeks ago.
Oh, right. Oh, you probably know more about it than I do in that case. You fill me in on anything.
Well, I mean, they talked about the Xenon reactor and WIMPs and what they're looking for, but they were very coy about results. They're doing a lot of other projects though, as well as the.
Oh yeah, they have neutrino detectors and other things there. But there was a paper, I say it's about a week and a half to 2 weeks ago, that was released. So maybe that was what they were being coy about. But
that would be right.
Yeah, there's about 4 or 5 papers that suddenly came out. They tend to publish them all as a group.
Thanks.
Great.
Okay.
Just by the by, Julian, have you switched on some magic button for subtitles? Because they've suddenly.
I think I have. Yeah.
Because I thought I knew Zoom, but yeah, that's great.
Oh, there we go. I think I've turned it off again.
No, it's fine.
It's still there. Ah.
Yeah. We've not used that before, but that's an interesting function. When you're sharing, you're able to do that when you're sharing, are you?
I think that's from PowerPoint, actually.
Because I don't think it's a Zoom function, but it's very interesting.
I don't know how to get rid of it.
Well, it's okay. Just don't utter any profanities and you're fine.
Right. Yeah, we just have to live with it.
Mark, I'll let you wrap up.
Thanks very much. Yeah. Well, once again, Julian, thanks.
I'll stop sharing.
very much for the talk. And for everybody, you've still got some opportunity to go and visit this comet and go and have a look to see if it's still naked eye. After all, it is the best Northern Hemisphere comet we've had since Hale-Bopp in '97. So if you haven't seen it, I would suggest you go out and have a look. And for those members, and there's quite a few, for those who've actually taken a photograph, it would be very nice if you could actually send them. You can send them to the Antares Astro Gmail account, and then we can coordinate it from there. So thanks everybody for your attendance. Thanks again, Julian. Keep enjoying your research at Nottingham University, and hopefully we meet up and see you again in the future. Thanks again.
All right. Look forward to that.
Yeah, hopefully we can get you over to Hereford, Julian, at some stage. Have you visited us in Hereford I don't think you have you?
I don't think I have. I have been to Monmouth though. So.
Yeah. Oh well, that's the other end. That's definitely a light second away. Okay. Thank you then.
Okay.
Do we have any other? Mark, do we have any other business?
Well, no, I think we covered all the things that we are going to do over the next month, I suppose. I mean, the ongoing thing is what we're going to do going forward in terms of continuing with the Zoom talks, because there may still be some reluctance by some to attend the Kindle Centre in any number. And also we need to discuss what we're going to do over our observing nights, because if we all descend onto a dark site, everybody wanting to look through telescopes, you know, you've got that worry as well. So it's a thing we've got to live with for a bit longer. So
actually, just before you go, Julian, I was going to ask you, are you finding now, because you're giving talks and you have obviously a set of talks, as you explained to us, do you find you're giving more talks than ever before at the moment, simply because you're not constrained physically by the distance and everybody's doing Zooms? Is this something which is increasingly popular, have you found?
It's sort of changed in some ways. So I'm doing about the same number of talks, I guess, but to different audiences. So for instance, to you, I've done one to a group in London, done to a couple to a group in Scotland, and one to a group in Chile. So
oh really? Well, there you go.
We've managed to.
But are you saying not necessarily to astro societies, a broader audience?
Usually astro societies. I used to give to people like U3A and like that. They tend to seem to have sort of shut down rather. Astro societies seem to be a little more on the technology front, although not all of them. Some of them have just said, well, we're going to sort of shut down until whenever. So I have offered to a couple of astro societies that I was supposed to be talking to. I said I'd do a Zoom, and they said, well, no, actually we'll wait till this is over.
Yeah. Well, at least they haven't asked us to wear masks on a Zoom meeting.
Not yet.
Imagine with this grid view. I've got the grid view. I can see everybody. We're all sitting there with our masks on. That would be bizarre. Okay. All right.
Like the cake, Rob B. Like the cake.
Yeah, that's Rob. Yeah. Okay. Right. Mark, are we done then?
I think we're done. Yes.
Okay.
So we'll see you all together again in August on the 13th.
Yeah, and thank you once again. Really enjoyed that, Julian. Great stuff. Thank you.
Okay.
Okay.
Right.
I'll call it a wrap. Thank you, everybody. Good night. Stay well. Stay safe. Okay. Bye-bye.
Thank you.
Cheers. Bye.
Thank you.